All right, it's Physical Science B Week 2. We're going to be looking again at Newton's laws of motion and also consider perhaps gyroscopic motion in case you were still a little baffled by that lesson you did. So to start off, I'd like your first lecture question to be what forces are acting on these guys? These guys are doing something crazy called, I think it's like sidewall skiing or something like that, where they get up on two wheels, the driver does, and then the guys get out and they change the tires, the front and back tires, while they're driving. Not something I would recommend you try. I'm sure that people have died doing this. But you know, kids will be kids, right? All right, so what forces are acting on these guys? You can pause the video and answer that question. A couple of the forces that you might have pointed out would be force due to gravity, pulling them down. Also the normal force, holding them up, so they're standing on top of this, and what's keeping them from accelerating to the ground based on that gravitational force is the fact that they are standing on their running board here, I guess, or whatever. So there's an equal and opposite force keeping them then in the same position, not accelerating one way or the other. If they weighed more, there'd be more normal force, right? They would have to be pushing them up to hold them up. Now, it's not necessarily important here that they're up on two wheels and on the side. I'm just sort of using that because it's a cute little drawing. But some other forces you might have noted would perhaps something happen to this guy's hair right here, right? You can tell that he's experiencing some air resistance. I wonder if these guys know they're so famous in my class. I wish they knew. So he's experiencing a force that's pushing him backwards. Well, why isn't he accelerating backwards then if he's experiencing that force? Why isn't that slowing him down? Well, it's because he's holding onto the car and using frictional force, maybe of his shoes, kind of leaning forward into the wind in his shoes, or holding on with his hands or something like that, to hold himself and apply a force to hold himself steady in the face of that wind. I'm just thinking of the guy in the salmon-colored t-shirt here, but I guess you could pick any of these people. So you can see there's at least four forces acting on this guy, sort of in different directions, and those forces are all conspiring to keep him moving along with this vehicle. And I guess it's a good thing he is, because otherwise bad things could be happening. All right, so keywords for today are force, inertia, momentum, and acceleration. We're talking a little bit more about Newton's three laws of motion. And then we'll start talking soon about his law of universal gravitation, and then some more complex topics like momentum, work, and power. Why are we doing this? Well, like we just did, we're applying the laws of motion and gravitation to describe the interaction of forces. And we just saw four different forces acting on this guy, right? And the resultant motion. In this case, the motion stays the same. It doesn't slow him down. Now, if the frictional force was more than the force pulling him forward, then he would slow down. Hopefully it would slow the whole car down and not just him, because if he did slow down and actually get separated from the car, then he would just be sliding along the pavement, and the only thing that would be slowing him down would be the road rash he was getting by grinding his flesh into the pavement. And that would slow him down much faster, but also be very painful. So question, why did this bridge actually collapse in the video? And the truth is we don't entirely know. But I wanted to show you this just to show you that it is complex, and there's actually argument about what the dynamic forces are on this bridge that cause it to collapse. The bridge that you looked at, the Tacoma Narrows Bridge, the original one, causing it to fall into the Puget Sound. You can see the new bridge here, and you can see all these structural supports underneath, right? Actually, that's the new bridge. This is the one that was built to replace it. And they didn't take any chances down here, did they? They were very serious about keeping this from fluttering. And that's what that's actually called, aerodynamic flutter. And in certain winds, at certain speeds, they think it's just the right speed of wind, maybe it was 40 miles an hour, it's going to reinforce the natural vibrations of the structure. And so they have to design structures like bridges and like this airplane so that stuff like this doesn't happen. You can see the fluttering of that airplane tail, which could be destructive. And so they have to design these things so that those natural frequencies don't get exacerbated by certain patterns of wind traveling at certain speeds, at certain densities, or whatever. And you can imagine it's kind of a similar thing to resonance, although they say it's not the same as resonance. And resonance works like this. You've probably heard of a wine glass being shattered, perhaps, when it hears the right note, yelled or screamed or sung loud enough to it. Well, the reason why that happens is because the glass itself has a natural frequency. When you ting, when you hit a wine glass, it's going to make a noise, right? And that's its natural frequency, the natural rate at which it wants to vibrate. And of course, that vibration is pretty small. But if you perhaps scream a note that is either that exact same pitch or maybe some exact like double the pitch or half the pitch or something like that, then you're going to send high pressure waves at that glass at the same frequency as it wants to vibrate anyway. So you can imagine if someone was screaming down here and these blue waves were sort of the sound waves coming out, and the high pressure was the blue, and you can see that each time the blue hits the glass, it's at the same moment when that glass is getting ready to move back, like right here. Oops, can you see my cursor? Right here. So boom, boom, it hits it. The sound waves hit it at just the right moment. Boom, boom. And if that high pressure wave is the same frequency as the glass wants to vibrate anyway, then it can begin to exacerbate that vibration more and more. And that's called resonance. And that's similar to what happened here in the bridge collapse. So we're not totally sure, but it's something like resonance because it was experiencing a force of wind, but that wind by itself wouldn't be enough to make it collapse unless it was exacerbating the natural frequency that bridge wanted to sort of vibrate or roll at anyway. So when you design things, you have to make sure that they're not going to vibrate or roll maybe at any frequency by introducing different structural elements to do that. So just a little more explanation on that one. So you remember, of course, Newton's laws of motion we talked about last week. Inertia, acceleration. So the first law is inertia. The second law relates force to a mass and its acceleration. And the third law simply says that forces never act alone, so that when you push a skater, you're pushing yourself backwards. And even if you're pushing an asteroid the size of Los Angeles, not only will you move backwards, but that asteroid will feel and have to absorb that push in some way, and it will alter its motion. So, an object in motion, this is Newton's first law, inertia, will stay in motion, and an object at rest tends to stay at rest. Does this guy have inertia? Answer that for your second lecture question. Now, you already know he has inertia because you know he's on the Earth, right? Spinning with the Earth, spinning around the sun, spinning through the moving through the galaxy. So he's moving at an enormous rate of speed without even knowing it. So he does have that inertia. But even if he was at complete rest, and somehow you could define total rest in the universe in some way, even though there's not really a reference point that's absolute in the universe, he would still have inertia, because inertia simply means even an object that could be at rest would tend to stay at rest. It would require a force to act on it in order to change its motion from being at rest to being in some particular direction. Similarly, of course, this guy has inertia as well. His inertia appears to be about to cause him some great humiliation, although, I don't know, maybe he's going to land this flip. I'm not really sure. I can't tell. It could be. Certainly the person that wrote this little meme, though, doesn't think he's going to quite make it. And again, his inertia is going to either be absorbed by his body slamming against the ground and getting hurt, or potentially by his muscles if he happens to land on his legs and his quadriceps can handle whatever force is then delivered. So they both have inertia. They both also have momentum then, which is simply a measure of the velocity they have coupled with their mass. So forces are the only things that can overcome inertia. So for example, this guy has a whole bunch of upwards inertia. But he had to be experiencing a force that overcame that inertia and slammed him back down to the ground and broke a couple of his bones. He survived. He was fine. Don't think he felt very good afterwards. So what happened to his upward inertia? Answer the question, lecture question number 3. And of course you know that gravity happened to his inertia. And gravitational force is constant, and it's causing us to accelerate about 9.8 meters per second squared down to the Earth, and so we need a normal force to hold us up, otherwise we would be accelerating towards the center of the Earth. So, next up, I want us to actually measure our own weight in newtons, because we're going to be studying and learning about things in newtons, and so instead of thinking about things in pounds, I want us to start thinking about them in newtons. So I'd like you to take your weight and figure out your real weight, or your weight in the metric system. So I weigh 175 pounds, and if we know that 1 kilogram is 0.68 slugs, and a slug is the unit of mass that we use in the English system, so if you are 0.868 slugs, you'll feel 2.2 pounds of gravitational force at Earth's surface. That means that if we want to figure out our mass m, over here in this F equals ma, in kilograms, we're going to have to take our weight in pounds and divide it by 2.2. So, for example, I weigh 175 pounds, and that means that every 2.2 pounds of that weight is going to be 1 kilogram. And the slugs thing doesn't really have to be in here, but I'm showing you that there is an equivalent thing to mass in the standard system that we don't use, which is slugs. We always, instead of measuring our mass, we measure our weight. But in the UK, you might measure your mass in kilograms, and you would say, I'm 175 pounds divided by 2.2, which if I calculate that out is about 80 kilograms. So that is my mass, m. So to figure out my weight, or the force of gravity acting on me, I just have to know then the acceleration due to gravity at Earth's surface. And luckily, off the top of my head, I know that's 9.8 meters per second squared. Or, in other words, my velocity will change by 9.8 meters per second every second if you drop me out of an airplane and let me fall. I'll be going 9.8 meters per second faster every second that I fall. So if I multiply those two things together, m times a, I'm going to get my weight in newtons, which is something like, I don't know, 780 newtons, something like that. But I want you, for your 4th lecture question, to figure out your weight in newtons. So all you have to do is have your weight in pounds, roughly. You can guess if you don't have a scale. Divide that by 2.2 to give you your mass in kilograms, and then multiply that times 9.8 meters per second squared, so that you have mass times acceleration, giving you your weight in newtons. So now you know that a newton is much less than a pound, right? Because if I weigh 175 pounds but I weigh 780 newtons, you kind of get an idea that even if something weighs a lot of newtons, that doesn't necessarily mean it's as heavy as you might think it is. So 1,000 newtons might only be something that's 220 pounds or something like that. And I did have a tree fall on my house recently, and I guess I thought I would show you that and have you think about the fact that this tree is currently a certain number of newtons, or was a certain number of newtons. It's not there anymore. I'll show you in a second, actually. It's maybe, we might say, 4,000 newtons, or actually it was probably more than that, probably 10,000 newtons, we might say. And that's what my house then has to, the amount of force my house actually has to exert on it to hold it up, because that amount of force is pushing down on my house. But was my house in greater danger at the moment of impact? And of course you know logically that it was, right? But that's because my house not only had to hold the weight, the force up, but it also had to stop the momentum or the inertia, again, those are kind of like two sides of the same coin. It had to stop the inertia of that tree that was falling. So it had to also absorb that inertia. So that required even more force up from my house. And my house was luckily able to handle that. And though it got a couple punctures in the roof, it didn't actually collapse. So that's how Newton's sort of first law of inertia and Newton's second law can kind of work together to magnify something. So we're going to look outside now. And I actually want us to consider a fidget spinner. Ooh, weird. And you've probably noticed before that when you spin these and then try to move them around, they do some funny things. They don't feel like you'd expect them to. Like, it's not like when you move them around and they're still. They put some weird forces on your hand. That's kind of like, it's weird to get used to those forces. And that's because of gyroscopic effects. And I'm going to show you a little bit about gyroscopic effects right now, so you can hopefully understand that lesson a little better that Derek Muller took you through when he was holding that weight up at the end of that stick. So let's go outside, have a look at something here. So you may have seen this before when you spin a wheel and are able to make it defy gravity, right? By the way, here's my house. It's okay. We actually cut the rest of the tree down too, that stump. All right, so I'm holding a wheel here. You can see the wheel. And you can probably guess, if I hold it like this, what's going to happen to it if I let it go, right? What's going to happen to it? It's going to fall. Or sort of fall horizontally like that. But what's going to happen to it if I spin it and then let it go? You would think that the same thing would happen, right? And probably when you first saw this, you were amazed that it did not fall. So here I'm spinning the wheel and now I'm letting it go, and the wheel is not falling. You'll be able to see that as it spins around here. Now what's the reason for that? That gyroscopic effect that holds that up. Well, the reason is because the acceleration that the parts of this wheel are feeling are coupled with the fact that it already has a certain amount of inertia or momentum. So you can imagine that if you have a ball, for example, if I have a baseball, and I throw a baseball, and that baseball is moving, and let's say someone like hits it or something like that while the baseball is moving, the baseball won't necessarily slow down. If you push the baseball, I might push it up, and the trajectory of that baseball will go from this to moving upwards like that, but it'll still be moving forward very quickly. It'll just also be moving in this direction at the same time, so it'll kind of go diagonally. So you can deflect the motion of an object moving straight. Well, the same thing is kind of happening here. If you break this wheel down into its different parts. So if you can think about the wheel, when it's like this, it's wanting to experience a force that's pushing this way, in essence. It's pushing this wheel down. But if the wheel is already spinning, let's say, forward towards you, well, then all you're going to do, you're not going to push it directly down, but you're going to deflect the wheel's motion. So this upper part of the wheel here is going to be moving forward, but as you deflected its motion to push it out, it's also going to be moving outward. So that then when this piece gets out to here, gets out to the front towards you, it's going to then be, instead of down, it's going to be out. So it's going to want to be turning that way because the motion it's already had is going to carry it to here very quickly, even faster than gravity could carry it. Gravity could not go as fast as this wheel is already going down. But as it goes down, the gravitational force it was feeling and kind of is still at any point up here is going to give it this deflection that's going to cause it to move out. So instead of falling down, it's going to move out and process around like that because this particular part of the wheel was deflected. It wasn't necessarily thrown down because, like I said, it was already accelerating downwards faster than gravity could accelerate. So if you think about that, then you would guess that if the wheel is spinning forward like this, and it's experiencing a force that's pushing it, wanting to push it out, as you deflect that force, just like the ball, you're going to cause it to move outwards like that. So it's going to process in this direction. So let's see if that actually happens, if the wheel moves in that direction when I spin it forwards. And we see that, yes, it does. It precesses in that direction. So in a sense, if you look at this from the top, you'd see it moving around counterclockwise. Now, if I spun the wheel the other direction, backwards, it would precess the other direction, because now this piece here that I'm deflecting forward is in motion, but that motion is going to be turning it out in that way, clockwise if you're looking from the top. So let's try that. And you can see that's the case again. Now it's precessing the opposite direction. And as it slows down, as the wheel slows down, that precession will be more and more pronounced, and it'll actually go faster and faster in its precession. Let's see if you can see that. So I'll slow it down here a little bit. And as I slow it down, the precession increases, the rate at which it spins or turns around.